So in today's video, we're going to look at chapter 8.5, which looks at assessing normality. So normally what we've done before is when we want to know whether a particular data set has a normal distribution, all we have done is we have plotted the data points against the frequency of each of the data points. And if we find out that that histogram, remember a histogram looks at frequencies, if we have this type of curve, this type of distribution, where it is a symmetric bell-shaped curve, we know that that data has a normal distribution. Okay, and that's where we have plotted each of the data points against the frequency. So that is the histogram. The thing is that when we do this and we are looking at the frequency of each of the data points or each of the classes that we've put our data points in, we really need enough data points in order to get that kind of shape to our graph, to our histogram. Okay, if you have a small amount of data points, it's very, very difficult to see this kind of shape occur on your graph because you don't really have enough data points to where you can really see an obvious bell-shaped symmetric curve. So we tend to say if we have less than or equal to 30 data points, so n being the number of data points, if we have less than or equal to 30 data points, we tend to use something called a normal probability plot instead. And that normal probability plot is going to tell us whether our data points actually follow a normal distribution. Okay, so if you have at most 30 data points, because it's very difficult to see from drawing a histogram with the frequencies of either the data points or the classes that you've put the data points in, it's very difficult to see those this shape of a curve come out. What we tend to do is to draw this normal probability plot. It looks slightly different to anything we've seen before, and it actually uses a formula that we did back in chapter 8.4. Because what it does is it takes each of our data points, x, and what it's going to do is plot it against this z value. We call it a z-score. If you remember back in chapter 8.4, we did something called a z-transformation. And that z-transformation used this formula. And what we did was we took each of our data points, x, and then we subtracted the mean from the data points. So for every single one of my data points x, I would subtract the mean. I then divided that value by the standard deviation. That gives me this thing called z for every single one of my data points. So for each data point x, I'm going to get this value of z. If I did this with every single one of my data points x, the z values that I get out then had a mean of 0 and a standard deviation of 1. That's why we did this z transformation, because we started out with our data points x having this normal distribution with some random mean mu, which wasn't equal to 0, and some random standard deviation sigma that wasn't equal to 1. And by doing this to every single one of my data points x, the data values z that I got back from this would then have a mean of 0 and a standard deviation of 1. And it was way easier to deal with probabilities when we had done that and transformed it into this standard normal distribution that had a mean of 0 and a standard deviation of 1. So that's why we did this. But what I can go ahead and do on this graph is I can plot each of my data points x against its z-score. So for each x, I'm going to subtract the mean, whatever that mean was for that data set, and divide it by the standard deviation. I'm then going to, for each of my values x, I'm going to get this z value out. That z value for each x is called a z-score. So for each x, I'm going to plot x against z for each of the data points x, okay? Now, think about what we are doing when we do this z transformation, when we figure out the z-score for each x value. Okay, think about what I'm doing here. I'm subtracting the mean. That tells me how far my data point x is from the mean mu, whatever mu might be. Then what I'm doing is I'm dividing that distance, the difference between x and mu, I'm dividing that by the standard deviation. Okay, so I'm just taking the distance between x and the mean and I'm dividing that by the standard deviation. What does that do mathematically? Well, that tells me how many standard deviations, so how many multiples of the standard deviation that x is away from the mean mu. Let me say that again. What this z-score does is it tells me how many standard deviations x is away from the mean mu. Okay, so it just tells me how many standard deviations I am away from the mean for each of my data points x. Now we know, just mathematically, we've done this before with the empirical rule, that most of my data points, in fact roughly 99.7% of my data points, should lie within 3 standard deviations of the mean. Okay, that tells me that I'm normally, for most of my data points, if I follow a normal distribution, most of my data points should be within 3 standard deviations of the mean. That tells me that my maximum z value should be around 3 and my lowest z-score should be around -3 because it's very unlikely that I'm more than 3 standard deviations away from the mean for any one of my data points. So for most of the stuff that you're going to deal with, z is going to be between 3 and -3. You may get 1 or 2 points here or there that may lie outside of that, but most of your data points should be within that range of z because we know that 99.7% of our data points should lie within 3 standard deviations of the mean. Okay, so now looking at kind of what this should look like in the middle, okay? Coming back to our normal distribution curve, okay? If our mean is down the middle, I know that I have some points that are going to be above the mean, any of my data points here, and some points are going to be below the mean, okay? Coming back to our z-score, our z transformation formula. When I do each of my data points minus the mean, I'm going to have some data points above the mean and some below the mean. If my data points are above the mean, so my x value is above the mean, then when I do x minus the mean, I'm going to get a positive value. Divided by, we always have a positive standard deviation, so divided by that positive standard deviation, I know that z must be positive. Okay, so I know that for any of my data points above the mean, that z is going to be a positive value. So I know I'm going to get some data points above. Then if x is below the mean, so for any of my data points that are somewhere down here, I know that x is below the mean, so x minus the mean is going to be negative. Divided by a positive standard deviation is still going to be negative, which is going to give me some data points below the mean. Okay. I'm going to have very few data points down here and very few data points up here. So the number of data points that I have that have a z-score of around 3 or -3 is very small. But the number of data points that I have that have a z-score where I've done x minus the mean, but x is closer to the mean, okay? I've got a lot more data points that are very close to the mean. They've got a higher frequency. So all of those data points have a higher frequency and they are closer to the mean. That gives me a z-score of close to 0. Okay, remember x minus the mean. If x is close to the mean, then this numerator is going to be close to 0. 0 divided by anything is still 0. So I know that I'm going to have more data points that have a z-score closer to 0 than I am for those that are going to be further away at 3 or negative 3. Okay, more of my data points are going to be around 0 and few of them are going to be out towards 3 and negative 3. The actual shape of the normal probability plot has a lot actually to do with the ordering of the data points, and it has to do with the number of the data points. We don't actually get into that with this class, but you should realise that you're going to have this whole deal where you've got some data points that are going to give you a z-score of close to 0, and a very few of them that are going to be further away from 0. What we actually say is, and again, you don't need to know the ins and outs of this, it is actually on the Learn section for 8.5 if you are interested in how this works mathematically. There is actually like a 4-step process that they lead you through of how to create this normal probability plot. But what you need to know is, if data follows a normal distribution, it means that its normal probability plot should lie in a straight line. Okay, so for any data, when you plot x, the data points, against their z-scores, you should find that if the data has a normal distribution, so it follows normal distribution, then the normal probability plot for that data should form an almost direct straight line. So you should end up with a normal probability plot that should, you may have one or two that may be slightly off, but for the most part, they should lie in a straight line where you've plotted each of your data points x against their z-scores. When you go ahead and do your homework, it is going to ask you to identify a normal probability plot where those data points have a normal distribution. And it's going to show you a variety of graphs. Make sure you go for the graph that has that direct straight line, okay, where your points lie in a straight line, because they will give you some that may look something like, maybe like an S shape, or some where you only have 1 or 2 points that lie off of the line. The one that lies in the most straight line is the one that's going to have that normal probability. Okay, it's going to have that normal distribution. As I said, we only do this if we have very few data points, okay? If you've got more data points, it makes more sense to use a histogram. You're going to have higher frequencies. It's going to be easier to see that bell-shaped curve occur. But when you have very few data points, it's very difficult to kind of get that shape going. So that's why a normal probability plot is used. You can actually plot a normal probability plot for your data points on your calculator. You probably won't need that for this course, but I'll let you know how to do it. If you go into stat plot, so you go to second and stat plot, it's where we actually did all the scatter plots and stuff very early on in the course. It's where we found the box plots. So you're going to go to second and stat plot. It's the one with the y equals function right at the top left is where you're going to find that. If you go into that, the very last option on a TI-84, where you go into the type of graph that you want, there's like scatter plots and box plots, etc. If you go to the very, very last option, it looks like a bunch of dots in a straight line. That is the one that is the normal probability plot. So the last option on the TI-84 calculator, when you go into second and stat plot, you go into any one of your plots and it asks you for the type of graph that you want. It's the very, very, very last option. out of all of them. That is the normal probability plot. If you did want to do that for a particular data set where you have very few data points and you want to know whether it has normal distribution. As I said, you probably won't need to do that for this class. It's very unlikely, but just so you know where it is and that your calculator can actually do that for you. If you do have any questions about where to find that on your calculator because you are interested, please just let me know in class and I'm happy to show it to you, but you don't need it for your homework or anything like that. Just as another heads up of something that you need to know with normal probability plots. Whenever you have outliers, okay, so you end up with 1 or 2 data points where you have a higher frequency for 1 or 2 data points, or where you have 1 or 2 data points that are way off of what the others are, okay? When you have that kind of thing happen in your normal probability plot or in your data points, okay, it's really going to throw off the normal distribution, okay? Think about it in terms of a histogram. Normally we have a histogram that has that kind of a shape. If you had a data point, let's say here, where you had suddenly 1 or 2 data points occur at that point that weren't there originally, that's going to cause a very, very odd shape to your histogram. You're going to end up with something that looks like that, and it throws off that normal distribution curve. Same for if you have something that is a complete outlier. Okay, if you had something that was a complete outlier, say up here somewhere, then you would end up with something that would look like that. And it throws off the normal distribution. Because of that, we don't like there to be 2 or more outliers. We will accept 1 outlier in our data, but we don't like 2 or more outliers because it will start throwing off our graph for our normal distribution, for our histogram or for our normal probability plot. So we only accept 1 outlier. Any more than 1 outlier we don't like because it's going to throw off our graph, it's going to throw off our normal distribution. So we don't want more than 1 outlier. Okay, so as I said, we will allow 1 outlier, but any more than 1 outlier we do not like because it's going to throw off our normal probability plot or our normal distribution bell-shaped curve if you go ahead and do a histogram, okay? Go ahead and try the homework for this. It is very simple. It's just a quick click-through type homework, so it shouldn't take you too long, and it is based on like, hey, here's a set of graphs, which one of these normal probability plots demonstrates normal distribution? Which one of these normal probability plots demonstrates a data set that does not have normal distribution? Okay, in which case it's going to be like when you plot out the z-scores against the x values, you're going to get like a curve to your line. Okay, so it's going to end up more like, I think I drew it somewhere. It's going to end up more like this than it is like a straight line. Okay, so anything that doesn't have normal distribution is going to have a curve. Anything that does have normal distribution, its normal probability plot will lie in a straight line. So it will ask you questions like that. It will ask you how many outliers you're allowed and stuff like that. So it should be a pretty quick click through homework. But if you do have any questions, let me know and I will see you in the next video.